Hey everyone, welcome back to this course on DC to DC converters. This week we're taking a look at input filtering and output filtering. And this is just a reminder of what we're doing, right? So we're reading this DC to DC Book of Knowledge by Steve Roberts. I need to update this slide, but next week, 8 August 10th will be our last meeting. I made some updates to the schedule. I took out the chapter on reliability, basically. And we're just going to jump straight into magnetics and transformers next week. These are just a set of questions as a knowledge check from last week, right? So last week we looked at a bunch of different protection circuitry, including reverse polarity protection, over voltage, over current, and under voltage in particular. So you should take a look at these questions, make sure that you can answer them, and then you'll be ready for an interview type situation. So jumping straight into input filtering. So these switching converters that we've been looking at throughout this course are sending pulses of energy. Each of these pulses are charging output capacitance, right? And that's just due to, right, we see that as when the voltage rises, that's actually just some amount of capacitance being charged. And then the load is taking that energy that's stored in the capacitor and causing the voltage to drop, right? So it's discharging that capacitance. And so this act of charging and discharging the capacitance causes a ripple voltage, which in turn causes ripple current to be coming, from our DC to DC converter. So we can actually reduce the amount of ripple current by increasing capacitance. Right, the more capacitance that you have, the slower the rate of change of that voltage will be. And so if you add more capacitance, naturally that ripple current will also decrease. So these capacitors provide a low impedance path for high frequency. And here I've got the equation for impedance of a capacitor. Right? And you can see if omega is our angular frequency there, that the higher frequency we are, the lower the impedance of this capacitor here, right? And our goal ultimately is to kind of get rid of this AC component of the current, and that happens through the equivalent series resistance, right? So the capacitor is helping to shunt all this high frequency energy, and then if we have a low amount of ESR, that also helps pull in more of that AC current, thereby reducing our AC component of the ripple current that gets to DC to DC converter and also to the load, right? If we're looking at output capacitance. So generally speaking, for these filter capacitors, we want a lot of capacitance and we want low ESR. But one thing that we always want to make sure is that we're not exceeding the RMS current rating of the capacitor. And so manufacturer data sheets will usually have this listed or have some sort of tool that you can use to figure out how much RMS current at a specific frequency that the capacitor can handle. And then one thing to note is that if you have capacitors in parallel, this will help distribute the ripple current, right? If we have these capacitors in parallel, we've now got two different paths for the AC current to flow through. And so the capacitors will actually share that RMS current load, right? So again, the RMS current going through each capacitor will be reduced by putting multiple in parallel. And you'll also often see multiple different capacitances, right? So not just a single capacitance value. And this is so that we can actually have a lot of AC current sinking at different frequencies, right? So here's that impedance equation for the capacitor again. And if you change the capacitance and look at a single frequency, then we can, pull in different frequency current. So both the input and output contain wideband disturbances. And this is on the right here is an example of a switching converter and looking at how much noise is being coupled back onto the connectors, right? So this is a form of interference that's actually leaking out into the world outside of your DC to DC converter. And this is often unacceptable, right? Based on different standards, we have different acceptable limits of these conducted emissions. And in order to stay under these limit lines, we need to have filtering across a wide band of frequencies. So here on the rightmost figure, you can see the effect of adding filters, right, significantly reduces the amount of energy across this frequency spectrum that's getting leaked into or outside of our DC to DC converter. And so these disturbances can either be common mode or differential mode. Common mode common mode noise, as you can see here on the right, has a symmetric pattern in the sense that all the current is flowing in the same direction and it's returning through this common ground here. Whereas differential mode noise or disturbances will travel in opposite directions, as seen on the left here. For example, right, we have our power and our power return path going between the source and the load. And so obviously, based on the type of disturbance that we're targeting, we'll need different forms of filtering. And we'll get into the different types of filtering soon. But first of all, how do we measure ripple current, right? Because that's one of the things that we're trying to filter out. And we typically do this with a shunt resistor, right? If we just use an ammeter, we actually can't really look at the specific frequency or the AC amplitude. It often gives a peak-to-peak value or an RMS value, but that also includes the DC component of the current, right? If we're looking just at an ammeter. So typically, in order to look at ripple current, we'll need an oscilloscope and we'll need to plot a voltage across a shunt resistor or have some kind of current probe. All right, so then jumping into output filtering. So as mentioned before, output filtering prevents interference from getting out. This is a little bit different than input filtering, right? We're preventing the interference from getting into our DC to DC converter with input filtering. And then here's just an example of a switching ripple, and you can see little noise spikes on it as well. So the switching ripple is typically a differential mode form of noise, whereas these little spikes here are usually common mode. And this is actually occurring usually from coupling capacitance, right? So whenever we have a change in voltage, there's some amount of capacitance between conductors. And then this change in voltage causes some sort of coupling into those conductors. And then you can see, due to that kind of stray capacitance there, we've got little spikes of energy here. And these are often random, or they appear more random, at least, than the switching ripple, right? The ripple is very periodic, whereas this common mode noise is coming across as more random, right? So it's just one thing to kind of look at there. So LC low pass filters are often used to filter out ripple. Here's an example on the bottom right of the impact of having an LC low pass filter. And as you can see, this voltage ripple is significant. I'm assuming this is voltage ripple. I took this figure from the book. I'm not entirely sure what they're plotting here. It's not the axes aren't labeled. But if we just assume that this is some kind of voltage ripple, then you can see that these huge spikes here are significantly reduced, and then even the periodic ripple is maybe cut in half or so. And one thing to note is a good rule of thumb for picking out a cutoff frequency of your low pass filter is to use 1/10 of the switching frequency. And so as you might recall from, circuit theory, when we have an LC low pass filter, that's two poles. So then that will cause the gain to drop by minus 40 dB per decade. So then when we move out, 10 times the switching frequency, then we've effectively gone down, right? That's a whole decade, right? Going up by 10 times that frequency. So then our magnitude has effectively gone down by 40 dB, right? So the signal or whatever switching ripple has been attenuated by 40 dB. And moving on to common mode noise, right? So this is an example of how we filter out differential mode noise, right? The ripple. There are two ways to filter out common mode noise typically, and this is either to short them out with these common mode capacitors or to use a common mode choke, which is this kind of inductive structure here. And the idea, right, with this common mode choke is that we've got two conductors and they're wound in opposing directions. And so the magnetic field works such that the common mode noise or any kind of common mode currents flowing through the structure will actually be dampened out, whereas the differential mode currents will just pass through without saturating the core. And so these common mode capacitors are just providing a low impedance path for switching spikes. For example, in this kind of isolated topology here, right? We've got a transformer here, so we couple the input line to the output line with this capacitor here, thereby providing a low impedance path for these high frequency spikes here. One thing to note is that if there are strict isolation requirements, sometimes you won't see these common mode capacitors here because that does allow some energy to leak from the input to the output, which can be undesirable for strict isolation requirements. And then I think this is the last slide I wanted to talk about. So predicting electromagnetic compatibility is difficult, right? So we're always trying to meet certain requirements in terms of radiated and conducted emissions. So one thing, we need to be able to, our DC to DC converter needs to work properly when it's subject to radiated and conducted noise, right? So for example, if I take my input line and I add some kind of signal on top of it, right, this is a form of conducted noise, then my circuit still needs to be able to work at certain levels of that conducted noise and radiated noise. And then also we need to be able to keep our radiated and conducted emissions below certain limits. So obviously we've got a switching converter here. So there is spectral energy right across the frequency spectrum. And we don't want that to leak out because if it leaks out, it can potentially cause other devices, upstream or downstream to start breaking. And we want to prevent that as much as possible. So there are often electromagnetic compatibility requirements in the form of different standards. And I showed them back here somewhere. Yeah, right here. So this is just an example. I don't know exactly. So here it says the EN 55022 class A limit and then the class B limit for the same standard. And you can see that by adding their filters, they were able to reduce the emissions to below those limit lines. And that's usually the goal with this different filtering that we include in our circuits. But with that, that's all I had to talk about this week. Thanks for tuning in. I'll see you guys in the next one.